So hi everyone. So today it's my pleasure to introduce Nicolas Martin from the Observatoire of Strasbourg. So Nicolas is really well known for many things. One of the things is dwarf-galaxies, other is M31. So he's a member of many surveys. So PANDAS, which is what he's going to speak about today. He's also the co-PI of the Pristine survey that we hear about a couple of seminars ago. He is also an active member of WIV. He is in charge of the target list selections for GL ILATs, and he is in many other surveys, such as Foremost, blah, blah, blah. Exactly. So Nicolas. I forgot to mention that Nicolas is in Strasbourg since 2012 as researchers, senior researchers, and before he has done his postdoc at Heidelberg, and he did his thesis in Strasbourg also before. So yeah, thanks.
Thank you, Guillaume. Thank you for the opportunity to talk here. I was trying to observe last week at the INT. It turns out that it's difficult to observe when you have snow, but it was beautiful up there. And so I'm also very glad that I'm visiting this week, so I didn't travel to the INT just to look at the snow, because we do have that in Strasbourg as well. So thank you, Guillaume, for the introduction. And indeed, I don't know if I'm known for many things, but one of the things that I've been working on quite a lot over the last 20 years is dwarf galaxies, and in particular the dwarf galaxies, the satellites of the Andromeda large spiral galaxy, our neighbor in the local group. And so what I want to do today is take you on this 20-year journey of what we have found dwarf galaxy-wise around M31, and what we have understood over time. And it's a really, really long process. As I was putting all of this together, I did realize that indeed it had been 20 years since we started looking for these dwarf galaxies, and it's the amount of time it takes to really start understanding the global properties of the dwarf galaxy system of M31. And so why M31? You probably know that there's been a bit of a revolution over the last 20 years in the number of dwarf galaxies known in the local group, in particular around the Milky Way. The good thing is that with Andromeda, we're able to have a second satellite system. And so we can start looking at differences and similarities between the dwarf galaxies that are hosted by these two large galaxies, and whether what we know of the Milky Way satellites is universal, or whether we should be careful about trying to propagate the information we learn very locally in great detail to systems that are further away. And so what you see here is the Andromeda galaxy. It looks like a really, really tiny picture, much smaller than probably a figure that is somewhere in the hallway, because it's in every astronomy institute. You always have a beautiful image of Andromeda. But if you go and look in detail around a galaxy like Andromeda, what you actually see in the stellar halo of Andromeda is this wealth of substructure that is coming from small dwarf galaxies, or fairly large dwarf galaxies in some cases, that have been wrecked by tidal interaction with the host, so Andromeda in this case, producing, for instance, this giant stellar stream, which is probably a galaxy like the LMC that has been destroyed over the last few giga-years. But you also see other streams that are smaller. Here, the color codes the metallicity of the structure, with yellow being quite metal-rich and blue being very metal-poor. And one thing that also jumps right away is all these small little blue or green dots. These are the dwarf galaxies around Andromeda. With this survey called PANDAS, we've been mapping this whole region around, looking at the streams, but also finding a wealth of small dwarf galaxies that we have been characterizing over the years. And so these look like this. If you take an HST image of those, the one that I'm showing you here, I think this is Andromeda 3, was discovered about 40 years ago. It's been done for quite a while, found on photographic plates, and that's one of the reasons why you see it on the HST image, because it contains a lot of stars. But a lot of these faint dwarf galaxies, if you look at an image, they're below the surface, below the sky brightness limit of the sky, and you have to actually go and resolve individual stars to find overdensity of stars to be able to discover these systems. But before showing you how we do that, let me just take a step back and ask the question, why do we care about dwarf galaxies? Well, I would argue that the cosmology is quite well known on large scales. And one of the new frontiers is actually looking at how we can use small objects like dwarf galaxies to try to constrain the cosmology and making, or at least testing different models of the universe that we live in. If we look at the distribution of galaxies on large scales in the universe with dark energy, dark matter, and a little bit of baryons, the baryons on large scales, we understand them well. They correspond to the distribution of dark matter in filaments and groups and so on. And if you look at the scale of a galaxy like our own, like the Milky Way or like the Andromeda galaxy, I'm going to interchange the two names every so often because they're fairly similar galaxies for all purposes here. You end up with something like that. The simulation that's been running here in the bottom right is a fairly old simulation now, the Aquarius simulation of a dark matter halo building over time through hierarchical accretion of a galaxy like Andromeda, like the Milky Way galaxy. And so if we could put some dark matter goggles on, we should see something like that, where you have a smooth halo here in the background and hundreds of small subhalos. And we think that some of these subhalos do contain baryons and are observed as the dwarf galaxies that I'll talk about today. But you may wonder, why do we really care about these dwarf galaxies? If you look at the amount of stellar mass in the universe, that's produced by galaxies of different masses, you see that most of the stars effectively of the universe are contained in very massive galaxies. It's your massive ellipticals, it's your Milky Way, your Andromeda, and so on. Once you start reaching things like the LMC, it's only a very tiny fraction of all the stars in the universe, even though there's more of these galaxies. They're so faint that they don't produce a lot of all the stars in the universe. And what I'm going to talk about is actually this regime here, where sure, there's tons of these very small galaxies, but they don't have a major contribution to the amount of stars produced in the universe. But I would actually say that this is something that is very positive, because it makes them very sensitive to the baryonic processes that we think we understand from galaxy formation. It makes these dwarf galaxies sensitive to the environment, to ionization, to a lot of things that we're trying to understand. And if we get the physics of these processes wrong, then we will get the number of these faint dwarf galaxies wrong. We will get their properties wrong. And so, in a nutshell, what a lot of us have been trying to do for a long time is to make this kind of comparisons. On the one hand, you have a model of what the cosmology tells us that dark matter should look like. That's what a lot of us are trying to go for. What's the property of the dark matter particle? What's its mass, for instance? And on the other hand, what we see is baryons. And so how do you reconcile both? And one way to try to test, for instance, just simply the number of subhalos here is to look at these dwarf galaxies. There's way fewer of them, but how do you populate them depends on the physics of galaxy formation and the cosmology behind as well. So one way we understand these dwarf galaxies better, one way we also find them is actually, a lot of it is based on the photometry, and in particular the property, the way stars distribute themselves in the column magnitude diagram. This is a plot from people in this building from a few years ago that is showing you the distribution of different stellar populations at a fixed distance. So effectively, if you have a cluster, you would have a single stellar population, a globular cluster. If you have a dwarf galaxy, you can have extended periods of star formation. And so you start seeing that different stars would distribute themselves differently in this column magnitude diagram. And so with the photometry with photometric surveys and deep photometric observations, we can learn a lot from these dwarf galaxies. The first thing we can do is discovering them. You can note here on the right that the stars don't randomly distribute themselves in the column magnitude diagram, so that helps us in discriminating particular tracers that can help us find detections at higher contrast. Once we have discovered them, we can look at the distribution of stars on the sky to look at the structure, so the size and luminosity of these dwarf galaxies. If we integrate all of the stars that we have in the column magnitude diagram, we can figure out the luminosity of these dwarf galaxies. And the ones I'll be talking about today have a total luminosity of 10 to the 4, 10 to the 6 solar luminosity, so they're quite faint. If we have the column magnitude diagram, we can use, for instance, the tip of the red giant branch or the horizontal branch to figure out the distance to these objects. And of course, if you're able to have a beautiful column magnitude diagram like this model here that goes deeper than the oldest main sequence turnoff of different stellar populations, you can basically reconstruct the star formation histories by looking at where the stars are in the column magnitude diagram. You can figure out that a dwarf galaxy has mainly formed old stars, or it has continued to form stars throughout the age of the universe. One way to look at that, in particular for the star formation history, is this very nice figure that I stole from a paper by Dan Weiss in 2014. What you see on the left is a local group dwarf galaxy that's about a megaparsec away, probably a bit closer than that. It's basically the distribution of stars observed with HST in this particular galaxy in the column magnitude diagram. And what you can do, for instance, is find what is the best linear combination of single stellar populations that would reproduce the observed column magnitude diagram, and you end up with a model like this one, which allows you to say this galaxy has formed stars more or less constantly throughout the age of the universe. What you have on the right is the cumulative star formation histories over time, and you see that this is, close to a straight line, which means that this galaxy has constantly formed new stars over time. This is kind of the grail. To do that, you basically need HST deep observations of a lot of the galaxies that I'll talk about, and we're starting to get there. But it is really like the final goal that a lot of us are trying to get on these dwarf galaxies that I've shown. And it's interesting because if you look, trying to make a link back to the cosmology, if you look at the star formation histories you get for the dwarf galaxies of the Milky Way, this is an example from the same paper by Dan Weiss and collaborators. You see the cumulative star formation histories for, I think, 8 or 9 Milky Way dwarf galaxies. And here they ordered by their luminosity, with the faintest one being these red lines, and the brightest of the dwarf galaxies of the Milky Way being these blue lines. And you can quite clearly see that there's basically two different behaviors here. You have those that tend to be blue, the massive dwarf galaxies, that have a fairly constant star formation history over time. Whereas the fainter ones, those that are very red, they tend to shoot up very quickly, they form all their stars very quickly, and then they stop forming stars. And so there's reasons why that might happen. For instance, it could be ionization, that just if the dwarf galaxy doesn't have a deep enough potential well, it cannot shield its H1 gas, the H1 gas gets reionized, and the dwarf galaxy has to stop forming stars because there's no fuel to form new stars. This has driven the idea that these, around the Milky Way at least, that the faint dwarf galaxies tend to be what I call old and boring, with quotes. So they formed their stars very early on, then they got shut down. It could be environment. It likely is reionization. That's usually a scenario that's preferred. But are these properties universal? If we go in other dwarf galaxy systems, now that we can finally hope to get similar quality data, do we find the same conclusion? And that's one of the things that I'll explore in my presentation today. So I mentioned to you that there's been a revolution over the last 20 years with finding dwarf galaxies in the local group around the Milky Way, around Andromeda. The main reason for all this has been these large photometric surveys, CCD surveys, that have completely revolutionized how we can map the surroundings of the Milky Way, how we can map the surroundings of the Andromeda galaxy. And these surveys, probably most of them by heart. It's the SDSS, Pan-STARRS, the Dark Energy Survey. Here you have the gigapixel camera from Pan-STARRS, which is more than 1 billion pixels. It's a huge field of view of a few times the moon on the sky. And it's because we have these efficient ways of doing really good, accurate photometry over significant chunks of the sky that we're able to find these small overdensity of stars out in a sea of hundreds of millions of stars, these small overdensities that correspond to new dwarf galaxies. And one part that I really like is to represent this revolution. I mean, it's a term that we use a lot, revolution, but if you actually look at the number of dwarf galaxies that were known as a function of time, the end of the 20th century is here. That's a pretty strong evolution here in the number of known systems. And again, it's fairly easy to understand. You have photographic plates here, where every time there was a new survey, like a Palomar survey of the sky, people would painstakingly look at little smudges on the images that would correspond to integrated light, and then follow them up. Whereas now, as soon as you have the SDSS first, and then Pan-STARRS and DES and so on, these CCD photometries, and suddenly you start finding this abundance of dwarf galaxies that were waiting for us to be discovered just below the surface brightness limit of the previous surveys. You also see that in the absolute magnitude of the dwarf galaxy, so the total V-band magnitude of these systems. So -5, -6 is about 10 to the 4 luminosities. Over here, you're at about 10 to the 5, and so on and so forth. You can see that the dwarf galaxies that were found before, they were clearly hitting a limit, which is effectively the surface brightness limit of the sky. And then we have CCD photometry. We stop looking at these dwarf galaxies as in integrated light, as low surface brightness features, and we start finding a huge number of them. This is for the Milky Way. I can show you the plot for the Andromeda galaxy. It's basically the same story. And that is thanks to the SDSS pan-stars, but mainly to the PANDAS survey that I'll talk a bit more about in just a second. You can also notice that compared to the Milky Way, we don't go as faint. That is easily understandable. M31 is almost a megaparsec away, so you're unable to find galaxies, for instance, that do not contain red giant branch stars. You just can't find them because the only thing that's easily reachable with these surveys at the distance of M31 are red giant branch stars. So now we have these significant samples, we can start doing a lot of exciting things with them. But before going there, I just wanted to show you a couple of slides about the Pan-Andromeda Archaeological Survey, which is this PANDAS survey that I've been alluding to earlier. It's a survey we conducted between 15 and 10 years ago with the Canada-France-Hawaii telescope, the CFHT that is on Hawaii. It's more than 60 nights of telescope time to effectively map the whole region around Andromeda out to a projected distance of about 150 kiloparsecs from M31 and about 50 kiloparsecs from its companion M33 down there. Every one of these little squares that you see is 1 square degree. It's the size of the megacam imager, and I would argue it's on the best part of the best site on the planet, and that allowed us to have an incredibly good image quality with this survey, also because CFHT runs in service mode, and so we could require really aggressive imaging conditions, and that's essential because if you don't have a good image quality, it's very hard to discriminate stars from galaxies in your images at the faint end, and if you can't discriminate your stars from your galaxy, nothing looks more like a dwarf galaxy than a background galaxy clusters, and so you start finding these hundreds of galaxy clusters, and you haven't made much progress. So this is the type of photometric data that we were able to gather with PANDAS. This is the CMD of the whole few tens of millions of stars in the PANDAS survey. And there's quite a lot of features in here. On the right here in the red, you have foreground Milky Way stars. These are dwarfs in the disk, dwarf stars in the disk of the Milky Way that are in front of our nose. On the blue edge here, you have stars in the halo of the Milky Way. So these are all contaminants for what we want to do. But you can also clearly see a huge overdensity of stars here, which correspond to red giant branch stars at the distance of M31. And that's what these different white lines correspond to. It's M31 red giant branches at different metallicities between Fe over H of about -2 and -0.7. And so you can see with a survey like this with just 2 bands, it's fairly easy to discriminate the foreground stars from the background M31 stars that you really care about. So that allowed us to, if I just go back one on this one, if you just effectively select stars along these 3 different stellar populations, low metallicity, intermediate metallicity, high metallicity, do a bit of post-processing to try to take care of the contamination, you end up with a map like this one that I was showing you earlier, which shows the density of red giant branch stars at the distance of M31, with the colors coding the different metallicities. And again, you see all these blue-green dots that correspond almost invariably to new dwarf galaxies. You don't even need, in a lot of cases, to run intricate search algorithms. You just plot the red giant branch stars and you find these dwarf galaxies. And so in particular here, the ones that should appear in green that looks like it's more yellow here on that screen are the ones that we discovered in the PANDAS survey. They kind of all over the halo of M31. The other ones that are circled in purple were discovered at the same time with other surveys like SDSS or specific targeted surveys. But we went from knowing maybe half a dozen dwarf galaxies within that footprint to now knowing 24, 25, something like this. And there's been also other discoveries further out from M31 in regions that were targeted in a more shallow way by, for instance, pan-stars or SDSS. And so we really had a strong revolution in the number of known dwarf galaxies around M31. I think the number right now is more than 40, whereas again, 20 years ago, it was about 10. We find dwarf galaxies, but one thing that's absolutely essential to do if we really want to understand the global properties of the satellite system is to determine the detection limits, basically, so whether we know what we find and what we don't find, especially because, for instance, the sheer number of dwarf galaxies down to a given luminosity could be tied to the mass of the dark matter particles. If you don't know what you haven't found, it's very hard to try to constrain these properties. And so that's beautiful work by a student working with me, Amandine d'Oliva-Dolinsky. And what she did is that she basically injected 500,000 dwarf galaxies in the survey. We run the search algorithm multiple times and to get a feeling for where we can go deeper or less deep in the survey. And one of the things you can see, this is the surface brightness limit of the survey for a particular size of dwarf galaxies. You can see a very strong change between the northern parts of the survey and the southern parts of the survey. There's about 1.5 magnitude per square arcsecond difference between the north and the south, which is quite significant. And you might be surprised by that until you realize that M31, which is in the center here, is at a declination of minus 20 degrees. So it's basically just below the disk of the Milky Way. So in the northern end of the survey here, you're 10 degrees from the plane of the Milky Way. And so you have more contamination from foreground stars. And that explains why it's harder to find dwarf galaxies up there than it would be in the regions of the halo down here, where you have less contamination from the Milky Way. Once you have that piece of information, but also homogeneous analysis of all the dwarf galaxies, in particular in pandas, and measure a lot of information like the distance, the 3D distance around M31, the size and luminosities, the radial velocities, deeper and deeper color magnitude diagrams, then we're in a position where we have these detailed properties for a fairly large sample of Andromeda satellites. We're in a position where we can start comparing these properties with what we see around the Milky Way, where we can study the dwarf galaxies, or we have studied the galaxies in greater detail for the last 20, 30, 40 years. And so in particular, I want to look at 4 different points. I won't go into the details of all of them, but is the luminosity function, the number of satellites you expect down to a given luminosity, the same around Andromeda and the Milky Way? What about the size luminosity relation of the dwarf galaxies themselves? Are they bigger around M31 or smaller? What about the dynamical mass of these systems? And finally, I'll spend a bit more time on the star formation histories of these different systems. And so the first point, what is the number of dwarf galaxies we know around M31? What is the luminosity function of the dwarf galaxies that we know around the Milky Way and M31? We can now finally do that because we have all these detection limits, so we can fold that into an analysis. We do full forward modeling of models through the detection limits and using the 24 known dwarf galaxies in pandas as a way to constrain our likelihood functions. And the conclusion here is that around M31, down to the luminosity about 10 to the 4th luminosities, that's not me. Is it me? That wasn't me. So around M31, if you try to count or forward model some sensible model, you find that down to this luminosity, you have between 100 and 200 satellites that are, we know 24, but if you fold in the fact that PANDAS does not cover the full virial radius of M31, and if you fold in the fact that at the faint end we haven't found all the dwarf galaxies because they're hard to find, these are the true numbers, or should be closer to the true numbers of satellites that are around M31 and awaiting discoveries. Interestingly enough, it's a factor of 2 or 3 larger than the number of Milky Way satellites down to the same luminosity. M31 has, down to the same luminosity, 2 to 3 times more dwarf galaxies. We also know that it has more globular clusters, also a factor of 3 to 5. I would take that as a very strong hint that M31 is more massive than the Milky Way, like the dark matter mass of M31 is more massive than the Milky Way. We also know that M31 has more stellar streams. It probably had a more active life compared to the Milky Way. So that's the kind of information you can hope to build from just measuring or inferring the number of satellites you have around the host. What about the luminosity function? Basically, the distribution of satellite luminosities as a function of, or number of dwarf galaxies per bin of magnitude, for instance, or per bin of luminosity. What you see here is this, we assume that luminosity function is effectively a power law, has a slope like a power law, and we find that in M31, we end up with these PDFs here on the right, depending a little bit on which model we assume. For the Milky Way, we find these this teal point and its error bar there. And so it looks like the luminosity functions of the two systems, the Milky Way and Andromeda, are fairly similar with the uncertainties we have. That teal point for the Milky Way has a significantly larger uncertainty than M31 because that analysis was done almost 15 years ago. It's definitely worth redoing to see whether we can start teasing out differences between the luminosity functions or whether they are effectively, they have the same distribution of luminosities than we find around the Milky Way. One thing that also comes out of the distances that in this case Alessandro Savino in Berkeley has measured from R. Lyrae for dwarf galaxies around M31 is that it looks like the distribution of satellites around M31, the 3D distribution around their host, is very anisotropic, What you see on this plot here is a view of M31 from above, with the Milky Way being there on at -800 on the x-axis. So the Milky Way is over there, and you look at the 3D distribution of the satellites around M31, and you find that most of them are on our side of M31 and not on the other side. Is that anisotropy real or not? It's true that it is harder to find satellites that are further away. So you would naturally expect some kind of anisotropy like that just from the detection limits. So again, with Amandine Deliva-Donansky, we've used the model that she's constrained, the global model that she's constrained for the M31 satellite system, to find that even taking the detection limits into account, we can very strongly reject that anisotropy is due to the detection limit. So it is some real distribution of satellites around M31. There's a real anisotropy that is a little hard to understand, but it looks like most of the satellites of M31 are on our side and not on the other side. You may, if you look at simulations, you expect that if you have a couple of galaxies like in the Milky Way and M31, you expect more galaxies in between than on the other side because they feel each other. But M31 doesn't have this kind of a very strong anisotropy. So it's something that I think we need to investigate now that we've confirmed that it is real, and try to understand better. Is it, for instance, that M31 is not at the center of its dark matter halo or at the center of its satellite distribution? That could be an explanation that we're currently investigating. So I mentioned these 4 different points. Briefly, I went over the first one. It looks like the luminosity function is compatible. The number of satellites itself is different between the Milky Way and Andromeda, but we probably understand that in a sense of M31 likely being more massive and therefore having more satellites. We looked also with the same forward modeling that Amandine has done. We looked at the size luminosity relation because there had been hints initially that M31 maybe had more large galaxies. We showed that it's not statistically significant, and what we think is happening is that because M31 has more satellites, there's more galaxies that are in the tail of the distribution, and that's what gave the impression 10, 15 years ago that M31 might have more larger satellites. If we look at the dynamical mass profile, there's a lot of work that's been done by Michelle Collins in Surrey. She showed that there is no significant differences in effectively the dark matter halos that these dwarf galaxies inhabit. Although again, we have a few odd cases around M31, but it might be because there's so many more satellites that we're able to find a few odd cases that we have more difficulty finding around the Milky Way. And so what I want to talk about and spend a bit more time on now is the star formation histories of the dwarf galaxies, because we've been trying more and more to really get a feeling for how the dwarf galaxies of the Milky Way and Andromeda have been building their stars over time, and we find some really interesting differences between the two. So this started with a project called the Islands Project that was PI'd by Evan Skillman using HST to get deep colorimetry diagrams of 6 of the Andromeda satellites with a choice of quote unquote representative 6 dwarf galaxies, different luminosities, different positions around M31, with the idea being that if you want to do 6 galaxies, it's about 15 orbits of HST per galaxy. So you better justify that you really need to do them all, or whether is it okay to just do 6 and have a global understanding of what is happening in the Andromeda galaxies. And so we start with these 6. And one of the key questions we're looking for is this idea that the faint systems are quote unquote old and boring, that they shut down their star formation very quickly, or that their star formation was shut down fairly quickly, maybe by the environment, by ionization. Does that hold for the Andromeda galaxies? And so the star formation histories that we were able to build from these beautiful colorimetry diagrams that reach the oldest main sequence turnoff are quite exquisite. And so this is the distribution of these 6 satellites in this cumulative star formation history plot that I've shown you before for the Andromeda galaxies. At first glance, it might look like they're fairly similar. Most of them kind of shoot up reasonably quickly, they flatten out. But then if you look at the faintest ones, for instance, this one, which is the faintest one that we have, remember that for the Milky Way, these were shooting up very quickly and then plateauing very quickly because we thought that they might have been shut down by ionization. This is absolutely not the case for Andromeda 16 here. That continues to form star. Maybe it's not constant star formation, but it does form star over periods of gigayears until eventually it runs out of gas. So this is quite different from this simple picture that I was building using the Milky Way satellites. It could be because we have an oddball here. But we wanted to know more. So again, it's incredibly costly to do deep CMDs for all of these systems. We're talking about anywhere between 10 and 20 orbits per dwarf galaxy. So we decided to first go for very quick snapshots where we have one single orbit per dwarf galaxy for all of the orbits that had no observations in the archive. And so you can't reach the oldest main sequence turnoff with that kind of observations, but you can reach the horizontal branch and get good quality photometry on the horizontal branch, which can give you some information about the age of the stellar populations present in your dwarf galaxy. And so combining with archival data, we ended up with 20 systems that are covering this whole range of luminosities. It's quite a beautiful data set. This is the 20 CMDs that we have in here. And one thing that struck us very quickly is the fact that if you look at the horizontal branch of these different galaxies, a lot of them have a very red horizontal branch. There's some of them, like this one, that has a very blue horizontal branch. And usually we see the horizontal branch also as an age indicator in this regard, where the bluest stars would be the oldest one, and the reddest stars would be formed later, maybe only 8 gigayears ago, until it becomes effectively a red clump, like you can see in some of those CMDs. And so that was quite intriguing. Before doing any star formation histories, we decided to do something purely empirical and something fairly simple, is just looking at the ratio of blue to red horizontal branch stars on these different horizontal branches, and look at this ratio, which in itself doesn't necessarily mean very much. It's not a quantitative analysis. It's really qualitatively, do we see a change in the ratios between blue and red stars on the horizontal branch? And if you plot the different galaxies as a function of magnitude or luminosity up there, you see that initially, if you're bright, you have a lot of red horizontal branch stars over the blue horizontal branch stars, so that ratio is quite low. Blue over red is quite low. So this is quite typical of what we have in the Milky Way. And then at some point, you expect that to shoot up because suddenly you end up having just old stars. So this ratio blue over red becomes larger. And it is indeed what we observe at around magnitude -8 or something like that. But we're still left with a lot of stars that have low ratios, and that is what I was describing before, is that you have a lot of galaxies, even at the faint end, that have a lot of red horizontal branch stars that were likely formed later. What is going on at 10 to the 5? That could be what I was describing, organization that shuts down star formation for a fraction of these systems, but clearly not all around M31. It could be the environment, that this is when these galaxies fell, or some of these galaxies fell in the hot gaseous halo of M31 and got stripped of their gas through Ramperscher stripping. This is something that probably requires some modeling to go much deeper. What Dan did as well, because he's bold, is that he decided to try to get star formation histories from the horizontal branch effectively, and the red giant branch of these systems. It's fraught with peril, because depending on which libraries of models you take, you're going to have different shapes for the star formation histories. It turns out that over the last 10, 15 years, there's been a lot of progress on the modeling of the horizontal branches, theoretically. And so we've shown here that we can actually get pretty good star formation histories, not as accurate as if you reach the oldest main sequence turnoff, but you can still get a lot of information out of sub-horizontal branch CMDs. And what you see here is one of the dwarf galaxies on the left. In the middle is the best linear combination of single stellar populations, so that you can effectively rebuild the star formation history. And on the right here, you have the residuals after that. And so this particular galaxy gives you this cumulative star formation history, like the ones that I was showing you before for the deep data, or for the Milky Way. You can change the stellar population models that you put in your analysis, and you will get systematics when you go from one model to the other. But as you can see here, Dan tried 4 different models. You kind of get the same rough picture when you do this kind of analysis. And so you can see that this particular dwarf galaxy has formed stars for quite a long time, until maybe 5 gig years ago, and then it ran out of fuel to form new stars. And so we can do that for all of the 20 dwarf galaxies for which we have sub-horizontal branch CMDs, and these are the star formation histories that you get. And so it's a bit of an overwhelming plot here, so let me drive you, and in particular show you this key message that I'm trying to convey, is that the faint dwarf galaxies around M31 don't quite behave like the Milky Way ones. You have a lot of these faint dwarf galaxies. These are fainter than Draco or Ursa Minor around the Milky Way, and you can see that Draco and Ursa Minor that have formed mainly most of their stars early and then shut down. That's not the case here. A lot of those have continued forming stars for quite a while around M31. And so here we do have a different picture from this old equals, or faint equals old and boring that I was trying to sell you at the beginning of my talk and that we see around the Milky Way. As a reminder, this is what we see around the Milky Way, where again, if you look at those that I've highlighted in red here, it corresponds to these very red systems that shoot up quite quickly with some variations, of course, but shoot up very quickly and then shut down at about redshift 2 or 10 gig years ago. That's not quite what we see around M31. So just to finish with a few slides, let me try to quantify those star formation histories. You might not trust star formation histories based on the subhorizontal branch. So let's try to simplify the problem and not look at the details of these different curves. Let's try to get just two numbers out of them. The first one, which is the time at which the galaxies have formed 50% of their stars. This is what I'll call tau 50 here. And so it's easy to get. You basically just draw cumulative star formation 50%, and then you just read off the x-axis what is the time at which the galaxies have formed that. By doing so, we're probably less sensitive to the particular wiggles in the galaxy than if you were trying to look at every different ages what we would get. And then the other number that I want to look at is tau 90, which is the time at which the galaxy has formed 90% of its stars. And the reason why we use 90 and not 100 is that there's always issues with blue stragglers in the colorimetric diagrams that look like young stars but could be rejuvenated old binary stars and so on. So let's just stick to 90% when these galaxies look like they have formed 90% of their stars. And so again, you draw the 90% line, and then you read it off the plot. So let's do this for the Milky Way satellites first. So it's a plot with a lot of dimensions. Let me just slowly drive you through it. What you see on the x-axis here is this tau 50. When have the Milky Way dwarf galaxy formed 50% of their stars? And on the y-axis here, you have tau 90. When have they formed 90% of their stars? And you see that most of the Milky Way satellites reside down there. They formed 50% and 90% of their stars a fairly long time ago, and then they stopped forming stars. There are some stars over there. These tend to be the bluer, more purple points. These are points that basically correspond to dwarf galaxies that are brighter. These are the brighter dwarf galaxies that I was telling you earlier. They continued forming stars through quite a long time during the age of the universe, and they only shut down a few gig years ago. Their time 90 is very, very small. It's 1 and 2 gig years ago when they stopped forming stars. There are lines to guide the eye here. The black line is constant star formation throughout the universe, throughout the age of the universe. And these lines here would be like an exponential decay, like a burst of star formation, exponential decay with a scale length of 2 or 10 gig years. So very quick star formation would be on this line, and longer star formation that slowly start with gas would be on this line. And so again, repeating what I've said before, if you look at the fainter satellites, which are orange or yellow in this plot, they're all in the bottom left. They are old and boring. They form their stars very quickly, and then they stop forming stars. What does this look like for the Andromeda satellites? It's almost the negative of that. There's this big rectangle here that doesn't particularly mean anything, except that this is a place where you have no Milky Way satellites, for instance, and you have a ton of Andromeda satellites. It's a really different picture that's built by these two. And there's two effects that are quite interesting. The first one is that a lot of the faint guys, and so of course we don't go all the way down to the yellow points because we just can't reach these magnitudes for M31. But if you look at the orange pinkish points, they're kind of all over the place. It's not like they discriminate themselves like they do for the surroundings of Andromeda, where they kind of all reside down there, and then you only have blue points over there. You don't have this old and faint equals old and boring picture for the Andromeda satellites. The other thing you may notice is that the T90 is actually quite a bit larger for the bulk of the Andromeda satellites. You don't have satellites, dwarf-spheroidal satellites around Andromeda that continued forming stars until a gig a year ago, like you have around the Milky Way. So they formed the bulk of their stars later, but they shut down earlier, effectively. So this picture that we might have built from the Milky Way satellites of how dwarf galaxies evolve and they get shut down by environment, ionization, and so on, might not be the full picture. And I would argue that we definitely desperately need to go look at other systems. It might be just simply the environment in which these dwarf galaxies are accreted as they fall into M31, how they fall into M31, when they fell into M31, that changes the star formation histories that they have. And so to conclude with just a couple of slides on the last 20 years, as I've shown you, we have now something akin to 40 to 45 dwarf galaxies around M31. I've focused on the 24 or so that are in the footprint of pandas because we can go deeper in this region. And we do have all those systems thanks to the systematic searches that we have conducted, but also many other peoples have conducted over time. And now we've also accumulated a lot of follow-up data. So we have a detailed understanding of the dwarf galaxies, not only of the Milky Way, but also of Andromeda. And this is particularly exciting because now we have two labs where we can go and look at what dwarf galaxies do and how they behave as a function of their properties. I've shown you that there's similarities, or I've mentioned at least that the size luminosity relation and dynamical mass profiles of the dark matter halos these galaxies inhabit seems to be quite similar between the Milky Way and Andromeda. But there are some very significant differences. The first one being just the sheer number of dwarf galaxies around M31 down to a given depth. There is 2 to 3 times more around Andromeda. And the second one is these differences between the star formation histories of the different galaxies. In M31, the dwarf galaxies formed the bulk of their stars later. They had more protracted star formation histories, but for some reason, they kind of all shut down 3 years ago. Is it because that's when they all fell in the hot halo of M31? Is it that the M31 has a hot gaseous halo that's more efficient at ground pressure stripping these galaxies? These are the things that, as a community, I think we should be investigating around these galaxies. To conclude with the future, this is the past 20 years. Where will we be in 20 years? Well, obviously, I don't know, but I can think of a few exciting things that are happening right now. Will it be happening in the next few years? We're now in a position where we can do I would say proper, detailed, statistically robust inferences on the global satellite system, because not only do we have fairly large samples of dwarf galaxies, but also we've done a lot of effort as a community to get the detection limits, to really understand what we can or cannot find. We have different surveys that overlap each other in some cases, and that allow us to test the quality of our results. We're getting deep, oldest main sequenced star formation histories for M31, both from HST and also in the future also with JWST, which will also allow us with these different epochs to hopefully get the proper motion and the orbits of these satellites around M31, and maybe tie that to these differences that we see in the star formation histories that these different systems have undergone. I'll remind everyone that there should be about 100 to 200 dwarf galaxies that are easily findable around M31. If you have a big telescope with a large camera, and there's a few of those on the planet, maybe we should now go back and expand pandas or go deeper, because we know that these, I mean, we've always known these systems were there, but it's quite striking to know that in this footprint, we know about 25, and there should be 100. So they should just be there awaiting discovery. And beyond the local group, I'm quite excited by the prospects of Euclid, of LSST, of the Roman telescope that will allow us to do this kind of analysis, but not only in galaxies within the local group, but to go out to a few megaparsecs and resolve the stars of individual dwarf galaxies out to these distances of a few megaparsecs. So then we can hope to look at what happens if, instead of having a dwarf galaxy system around a spiral galaxy like the Milky Way or Andromeda, what happens if you have an elliptical host with a different accretion history? What happens if you look at smaller galaxies like Magellanic galaxies in the field? What is their dwarf galaxy population, and so on? And so I think there's still a lot of work to come from this particular field, and I'm pretty excited about the coming 10, 20 years as well. Thank you very much.
Thank you, Nicolas. Questions?
Hi. Formation histories that you find between M31 and our galaxy. So as you have seen, I mean, as you have shown here, the stellar halo M31 is quite prominent, and therefore it shows that it has gone through a lot of accretion activity. So you would expect a lot of your satellites, the satellites of M31, to be accreted by the galaxy itself along the history of the galaxy, right? So I wonder whether you do not find more all objects because simply they have been accreted, they have got enough time to be accreted in comparison, for example, with the Milky Way, where maybe they have been living there for longer because they have not suffered the tidal field or so. So do you think that the different dynamical histories of the satellite around these two galaxies could be also compatible with what you see?
I don't know exactly what is. It is possible that, for instance, some of those satellites that have continued forming stars for a while around M31 are on particular or benign orbits that keep them quite far away from the Milky Way, and that's why they haven't been destroyed yet. There's no strong evidence of a lot of young stars in the halo of M31. So if galaxies that had formed young stars until 1-2 gig years ago had been destroyed, then we should see plumes of blue stars that are just in streams, and we don't see that. More globally, in the comment you made, I think that it's probably coming from there, is that the environment is different, the way the galaxies were accreted is different, the fact that just the mass of M31 is different, probably has an impact on the orbits. The fact that the hot halo is probably denser, I would expect, means that you probably stripped more efficiently these galaxies. I would naively go more this way, but I think these are all open questions that we need to understand to really make this distinction or understand these differences between the Milky Way satellites and the Andromeda satellites.
Yeah, thank you for the excellent talk. Really tell us quite a lot about these differences. In fact, I want to ask you about the metallicity differences.
There aren't metallicity differences as far as we can tell. So it's definitely harder to measure spectroscopic metallicities at the distance of M31, but this is work that Michelle Collins and Suri has done a lot of work on. She's been doing a lot of work on the spectroscopy we've been gathering on all these systems. And if you look at like a stacked spectrum for all the red giant branch stars we get from these systems, the galaxies fall on the luminosity metallicity relation that we observe in around the Milky Way. So there's no strong difference, but this is, if there were a difference of 0.2 dex or 0.3 dex, we wouldn't necessarily see it, I think.
I thank you. A very excellent talk, and I'm outside the field, so I have some naive questions. First, continue the metallicity question. It's about I saw a mapping about the metallicity, right?
Yes.
That is obtained from the spectroscopic, no?
No, so the map, so this kind of map you're talking about?
Yes.
Yeah. So what we do here basically is that we use this colorimetric diagram. We assume that all the stars we care about are at the distance of M31. And so effectively they should fall, if they're metal poor, they should fall somewhere here. If they're intermediate metallicity, they should fall somewhere on this line. And if they're metal rich, they should fall on this line. And so we basically build like that. We just do 3 density maps around these 3 isochrones. And that's what allows us to get this particular map here where you see the density of stars, because here we're talking about definitely many hundreds of thousands of stars, and it would be impossible to get the metallicities very efficiently. We have metallicity for a few thousand of stars in the halo of M31. We've mainly targeted the different streams, and this is roughly consistent given the assumptions we make on everything being at the same distance and so on. So we do confirm that these differences that you see in this map are actually real differences we see in the spectra of individual stars as well.
Okay, and the difference between here, the metal poor and metal rich, is around 0.0.
No, it's about 2 dex, I think. So metal poor is about -2.
Okay.
And I think metal rich is like -0.5 in this map or something along those lines.
Okay. Another question is about how do you determine the distance of those dwarf galaxies?
Yeah, so there's 2 different ways. The way we started when we had just the pandas data is that if you look at a colorimetric diagram like this one, maybe this one is not heavily populated, so it might be a little harder to see, but effectively the red giant branch of this particular system, it kind of plateaus at -4, and so that's what we call the tip of the red giant branch, and it is a good distance indicator. So it depends a bit on the metallicity, but which is effectively the color of the red giant branch. But with the pandas data that at the distance of M31 basically reaches roughly the horizontal branch here, we're able to get the distance of all the dwarf galaxies using the tip of the red giant branch. And now that's been superseded by work by Alessandro Savino and Dan Weiss in Berkeley, where what we've done is that we've used the R Lyrae of these systems because we have deep HST observations of these different galaxies, we made sure that the different epochs were separate enough that we could find these RLRE stars, which are pulsating stars with a period of about 10, 12 hours. And using the fact that there's a handful to dozens of RLRE per system, we're able to get distances accurate to about 20 kiloparsecs for every single individual galaxy. And that's how we're able to look at the 3D distribution of galaxies around M31, fit a global model that includes also variations of function of radius from M31 and not just the Milky Way. But that's been a huge amount of hard work, convincing tax that we could do something really interesting with these deep data. And then the beautiful work that Alessandro did by extracting the RLRE, fitting them and getting the distance of these systems. It's very beautiful work.
Okay, thank you.
Okay, so I have one about the 90-50 timescale for the star formation history. So might be possible that this is due to, and it's going back a bit to what was Ignacio, due to the accretion history of M31 and the Milky Way, where some of them, like you have another density basically in M31 60 years ago, which correspond more or less when arrives the progenitor of the giant southern streams. And in the Milky Way, we start to get more stars, dwarf galaxies around 3 gigayears that have been shut down there, which correspond more or less of when arrives the LMC. So do you think it might be related to this?
So I think, so the LMC, I'm not sure I would go that far, but if you look at, let me just go back to the map I was showing before so that we're all on the same line. This giant stream that you see here, yellow stream that you see below M31, here, as I was mentioning, is probably a galaxy like the LMC that fell into M31 maybe 4 to 6 gigayears ago. And it's not just this giant stream or this fanning structure that it created, but these different shells that you have around the disk of M31, it's quite clear that the different wraps of that particular stellar stream. And so indeed, this happened 4 to 6 gigayears ago. I honestly wouldn't be very surprised if once we have the orbits of the dwarf galaxies, we find that a lot of them might have fallen in with similar orbits or at around the same time. And then, as you say, that could explain why you have this group that just shut down at the same time. It's because they all fell in the hot gaseous halo of M31. It turns out the giant stream has a very elliptical orbit, so maybe the other ones also have a fairly elliptical orbit. It brings them close to the center of M31, where the hot gaseous halo is actually quite dense. They get stripped of their gas, and then they stop forming stars if they haven't been disrupted.
So you get the orbits of the streams based on the simulation of Faraday?
So the orbit of the stream you can do quite easily, because this is more than 100 kiloparsecs on the sky, and actually you see that there's a distance difference. So this bit here is 150 kiloparsecs behind, and so with the combination of the change in distance and the change in radial velocity, you don't have a lot of options for orbits that fit these parameters within a sensible potential. And so even though we don't have the individual orbit of that stream, we know that the proper motion should also go in the direction of, I mean, we know where the stream is going, right?
No,
but for the,
because such a massive accretion will also shift the Milky as a Andromeda galaxy, and so we can generate this asymmetry, blah 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 that we're mentioning.
Absolutely, yeah. So one of the things that I'm interested in as well is this offset, it's anisotropy in the distribution of Andromeda satellites around M31. Could it be that M31 is just not in the center of its dark matter halo because it just got kicked by something quite big that came in, and not really kicked, but dragged it through gravity one way or the other, and at the moment it's kind of resettling back in the middle of the satellite system. These are things that hopefully we can investigate either through modeling, of course, but also through the orbits of these systems that we hope to get in a few years with GWST. That would be pretty exciting.
All right, thank you. Okay, so if there is no more question, thanks Nicolas again.
Thank you.
And, see you on Thursday for the next seminar.